All right, so for problem number 1, it says convert the 3-stage amplifier into an equivalent 1-stage amplifier. Determine the resulting input resistance, output resistance, and gain. Assume the ROs are not negligible. So the ROs, it means like these output resistors right here are not negligible. Okay. Okay, so in this case, let's see which one works. It's good. Okay, so in this case, so we have 3 stages right here, right? Each one has a voltage-controlled voltage source, okay? We have this input right here, this output, and we want to convert this whole thing into a 1-stage, and the 1 stage looks like this. It just looks like one of them, right? So, yeah, like for example, it'll look like this. It'll be the R out. Here's a R in. Here's a V in. And here's a V out, like that. Okay, so we want it to convert to be something like that. Oh, and we have to determine what this is. So you have some kind of gain here multiplied by your input, like that. Okay, so so basically what we'll do is we'll look at all of the gains going through there. Okay, so let's start right here. Now let's assume that there's nothing connected right here, right? So this is open right here. What's this going to be? So you have this kind of input over this, this output over that input, right? So the gain here is just going to be your A3. You guys see that? At that stage is just A3 for that gain. Okay, so if you don't see that, look at this right here. V out over V in. Okay, so if you look at your output voltage is going to be A3 times VI3. You guys see that? This right here? This is going to be your output voltage right here because there's no current drop. So it's just going to be this voltage right there. So that's going to be your output. So A3 VI3. And of course, over your input, well, your input is just this right here, which is just going to be your I3. These cancel out. And so output over input is just A3. That's how it is on the first one. The last one. Now before that, you have this situation right here. Okay? So when you're looking at this output over that input, you're going to have this. Okay, so let's do it output. So this V2 to 3 right here, we could use some voltage division for that, right? So it's going to be this divided by these two together multiplied by that. Okay, so that output here is going to be this R I3 divided by RO2 plus RI3, right? Multiplied by this right here where you're starting from, which is A2 VI2. Okay, so this is the output. The input is going to be this right here, which is just your VI2. So these cancel out. So you see how it's going? And it's a pattern that goes through each one of them. So that means we already know what this one right here is going to be, right? So that's just going to be this A1 multiplied by this fraction of this Ri2 divided by Ri2 plus Ro1, okay? And that's it. Okay? So this is AV of the whole thing right here. All this right here. You guys see that? So these two are exactly the same. The last one doesn't have any resistors in it because it's open. There's nothing connected to there. Okay? Now, this right here corresponds to the gain over there. And now for these right here, the output and the input, well, the input is just the first one it experiences, right? So that's going to be Ri1. So this is Ri right here. And Ro right there is just going to be that one right there. So looking in this direction, that's what it experiences. So Ro3. Okay. Well, let me do this. Yeah, AV. So that's what this is. Okay. Any questions about this? I gotta use my fingers to do this one. Okay. On this one right here, it says, what are the Y parameters of any one of the stages are, in problem one. Yeah, so if any of those stages in problem one, yeah, so this is worded in a way where if you don't get it right, like that part right, at least, just using one of the stages. So what are the Y parameters? So we're going to do the Y parameters of this right there. Okay, so for the Y parameters, that's just KCL, right? So we're going to look at I1 and I2. So I1 and I2. And they're going to be expressed in terms of these currents. So this current right here is being broken up into this current and that current. This current right here is being broken up into this current and that current. So the current going in this direction is G1 V2. And the current going in this direction is 1 over R1 times V1. That's what that G is. So this is the conductance right here. Okay. For I2 over here, we got this current, which is G2 V1. I'll put it over here to keep the linear combinations the same. And going down that direction is 1 over R2 for conductance, not resistance, times V2. Okay. And of course, if you want to make it look like one of the stages here, you see that if you want to, you can put this in, that's Thevenin, that's Norton. You can change that if you want to, put in, yeah, so you could change it and put in Norton or Thevenin, whatever you like. And this one is missing the source. So when you change this from Norton to Thevenin, that means that the voltage source is going to be 0. That's the only difference, but that's the trivial part. So wait, do you guys know how to convert from Norton to Thevenin? Anyone not know how to do that? Okay, sure. Okay, so let's say you have this black box right here. Here's your resistance, and here's some voltage right here. So this right here is the Thevenin convention, and that is entirely equivalent to Norton, which is like this. That's I, and this R. But the trick is you have to determine what I is from this. Or if you're here, or if you're starting here and going this direction, you have to determine what V is according to that over there. Okay, so you're going to start here or there. You can see that the resistances are the same. So for example, if you're looking at the resistance, looking at it from this direction, right there, that resistance this is the only resistance it sees, okay, going this direction. If you're looking at the resistance here in this direction, then what happens is that this has infinite resistance. If you could think about it like that, having infinite resistance. This has like no resistance, but this has infinite resistance. So what happens is that the current is going to go down this path and go back out for the resistance path, okay? And they're in parallel. So the resistances are going to be the same. So to determine the voltage here, you're just going to use I and R, and that's going to be the value of voltage. If you're starting here and going there, then your current is just going to be using your voltage and resistance, so V over R. And that would be the value of that current source on that side. Okay. But the thing is looking at it from the outside, if that's a black box, you cannot tell if it's Norton or Thevenin. You just can't tell, okay, till you open up and look inside. But you use those to, if you want to reduce your circuit, sometimes you need to switch back and forth between the two to like combine resistances together. And then you have an overall resistance, which is whatever the R is, in an overall source, which is the voltage or the current. Okay, on this right here, it says, if the op amps in the following circuit are non-ideal, then what is AV? So for AV, it is the overall output divided by the overall input. So now they're non-ideal, so you're going to have to consider these, the gains that's listed on them, okay? Non-ideal. And also you know this for non-ideal, that AV is A ideal multiplied by this right here. And we know what T is, the loop gain, that's A beta, right? Or you could just write it like this. Okay, is that for negative feedback or positive feedback? Negative feedback, right? If that was positive feedback, that would be minus. Remember? Okay, so these are like negative feedback systems, and that's what makes them stable. Okay, so let's figure out what each one is. Now, this right here is for each one. So, I should call this, AI for A1V right here, A2V for there. Then you multiply them together for the overall gain. Okay, so let's look at beta. So Um, what is beta for the first one right here? Let's call that beta 1. Okay, well, let's do it this way. Let's follow that. So what is what is A1? Oh wait, that's a bad way to say it. What's AV for the first one? Okay, well think about it this way. If that's ideal, what would it be? Exactly. So that would be 1 plus R2 over R1. Is this whole thing negative or positive? You guys remember? Yes, positive. Because it is a non-inverting amplification. What about the second one? What's that ideal gain? Is what? Yeah, negative. So, and the feedback is R4? Yeah. Exactly. Okay, so we have the ideal parts. Okay, and those are the ones that go right here. Now we have to find out what these are. Well, we know what A is. That's given to us. For each one, you know, we have the A's right there. So for this first one, well, let me scoot this one over a little bit. Okay, so for this A, it's just A1. We have to find out what the B is. 1 plus A1. So the B, well, the beta goes here. So that's the question. What is the beta? Okay, so beta is like the gain for the loop going backward, back through this thing. So going back like that, or going back like that. Okay, so what that means is that for the gain going back, that's the output and that's the input. Okay, instead of, you know, the other way around. So for the first one, R2 over R1 plus R2. And for the second one, R4 over R3 plus R4. There's a 4 here. And so A2, beta 2, 1 plus A2, beta 2. Okay. Now, if you don't see that, then what you could do is do KCL and do output over input, right? So what you do is do, like let's say you didn't remember, you know, your beta, is that the feedback or not? You know, and then so you'll know if it's R3 on top or R4 on top. If you don't remember, then let's do KCL right here. That's ground. You got that current and this current. And just do KCL, and then that'll help you out to determine what beta is. Okay, so this is the whole thing right here. And this is AV. Okay. Yes?
For the overall, do you multiply those two together, or?
Oh yeah. That whole thing is all multiplied together. Yeah. So it's like gain times gain. So first you have that first gain of your first op amp, and then whatever that gain is, that's going to go feed into the next one, and then you're going to get another gain. So yeah, everything's being multiplied together there. Okay, on this one right here, it says, given the two-pole low-pass filter below, if the capacitor C2, which is right here, is 0.00, I should just put microfarad, 0.001 millifarads, and the frequency F0 is 10 kilohertz per 2 pi, then determine the values of C1, R1, and R2 that are required to get maximally flat frequency response. Okay, so a picture is given to you. So which of these four curves is the maximally flat frequency response? Yeah, 1 over square root of 2, right here. You see that? It's maximally flat. See, now this one, it starts going up right here. This one starts going up. This one is not even flat. It just starts going down immediately. So this right here is the one that's maximally flat at that Q. Okay, and this is the 2-order low-pass response curve that's being plotted over here for different values of Q. Okay, and the frequencies right here are all the same. Okay, all right there. These right here, that's not resonating, that's not resonating. Okay, but these right here are. That's the omega 0. The omega that's being plotted along the x-axis are in here, j omega. Okay. So you're given a couple of things. You're given the frequency right here, and so you know that omega 0 is 2 pi f. That's why I stuck a 2 pi there, so they cancel out. This capacitor right here, that's given to you, so you know this C2. Okay, you know that. Now, this doesn't really help us very much in determining what these other things are, but you have these two equations. And, oh yeah, you found out what Q is. So you know Q, you know C1, and you know omega. So how many unknowns do you have here? 3. How many equations do you have? Where's the third equation? Okay, yeah, you do have a third equation, but yeah, I know you know. Yeah, so that's the problem. You have 2 equations but 3 unknowns. So what can you do? Well, you can come up with a third equation, right? Or you can put a constraint on something. You can say, well, I got 2 resistors here. Let's assume that both of the resistors are identical. Okay? That could be a constraint. If they're both identical, then what happens here, like if you make them both R1, then you just have 2 R1, 2 times R1. And so if you do that, then all the R2s go away. Then you have your 2 unknowns, 2 equations, and that's all you need. You guys see that? There's nothing wrong with doing that because you have free. I mean, you have 3 parameters, and you're free to choose. So as a designer, you just put a constraint on one, or you could say, well, I have an R2 laying around in my resistor box, and it's so many ohms, and that'll be your constraint. And then your R1 is then unknown or something. I don't know, but any of those will be fine. So 2 equations, 2 unknowns. That's actually enough to solve this whole problem. Okay? That's all you do. So if you want to figure out the number, you put your 1 over square root of 2 here. You put your 10 kiloradians per second here, right? That'll be R1. That'll be R1. That's 1 unknown. Your C1 is given to you. No, your C2 is given to you. So you just have your R1 and C1 left over in this equation, R1 and C1 left over in this equation, and then you'd be able to solve for one or the other. What you would do is like plug in one equation into the other one for C1 or R1. Yes?
Back on the previous question, I had a question about your data.
Okay.
Should it be the other resistor on top of both of them? The R1 instead of R2 and R3 instead of R4?
So you're saying it should be this right here. Might be right about that. Yeah, I think you're right about that. Yeah, thanks for that. Thank you very much. Okay, so for this one right here, given the pair of switch capacitor filters, what must be true about them? Okay, so you have some choices here, and I think I have all possibilities. So basically, you want to determine the direction of these, and also if it's an inverter or a non-inverter. Okay, so now remember how these work, right? They operate out of phase. So either the phi ones right here and here, when these right here are both closed, so current is able to pass through them, then these phi twos are both open. So they become like open switches and nothing can pass through. Same here. When these two phi ones are both open, these two are both closed. I mean, when these two are both open circuit, these become a closed circuit and they go straight to ground, and vice versa. So when these are both closed, open, where these are not going to ground, it's like an open circuit, then these right here are both closed, and so the path can go through here. And by looking at what happens to that, you can determine what direction the current is flowing. Okay, so for example, let's say the phi twos, let's say they're both open. Okay, that means they're not there basically. They're both open. That means it's open circuit. There's nothing allowing it to go to ground. And these two are both closed. So basically, you have this capacitor charging up from the voltage. So if you think of a positive current going this direction and charging up, that means if negative is going there to meet the positive, then you have the effective positive flow going this direction. And so it's going this direction right here. Okay? So that's what happens when both of these are closed. And then you flip it where then both of these are open and these are closed. So now you're going to ground and there's no path to go out of this. So once these are closed, closed and going to ground, then any charge there just goes to ground. And then current stops. There's no current at that time. And then they switch back and then current starts going this direction again. So this current keeps going around like this, but it goes in this direction. So if current is going in this direction, is that an inverter or a non-inverter? Why do you say inverter? I heard inverter. Yeah, because that's ground, and if positive current is going across this thing right here, it's going to go downhill. So that voltage is going to be lower than 0. Okay? So that's going to, so there's like a negative there, so it's inverting that signal. Okay? So that means that this is good. It's pointing in the right direction, and it's an inverter. And this is good. So we've eliminated these, and also we eliminated all those. So it's got to be these two, one of these two. Okay, so then what you do is just see what happened on, what's going on in this one right here. So on this one, when that switch right there is closed, and these are open, so when that's open, and that's open, and when that's closed right here. So in this particular case, when this is charged, when this capacitor is charging up, right here, it's coming, charges are coming from the ground, right? And nothing's flowing this direction. Then when these are both open and these two are closed, then current is finally able to go in this direction. So that means that this right here, for positive sense, it's actually pointing the opposite direction. So that allows us to say, well, it's not going to be this, it's going to be this. You see what I mean? And also, since the positive current is really going that direction, and that's 0, and it's going downhill, that means this has to be a higher voltage in order to go downhill and get to 0. Okay. Okay, on this one, oh, it was the first one, 5A. Okay, so for this, you have a 3-bit flash analog to digital converter right here. How many more resistors and comparators do you need if you wanted to increase? That's bad. If you wanted to convert it to a 4-bit flash digital to analog converter. So it says 3-bit is shown. See, 1, 2, 3. And then what you could do is just look at that to get your formula. So you have all these comparators right here. You have 1, 2, 3, 4, 5, 6, 7, 8 resistors. 1, 2, 3, 4, 5, 6, 7 comparators. So you could say this. If it's 3-bit, that's 8. That also equals the number of resistors you have. So the number of resistors equals that. And the number of comparators is less than that. So you could say 7. So if I wanted to increase that to 4-bit, then this would go from 3 to 4, right? So that's going to be 16. And this right here is going to be that minus 1. That's going to be 15. So you need 8 more resistors, and you need 8 more comparators. Okay. Following circuit is a quadrature oscillator where its loop gain is given right here. However, resistor RF is tunable via potentiometer. If all other values are known, I was really going fast with this. Then, what must RF be in order for the circuit to oscillate? I'm very sorry about this, my typos. And what will its frequency be of oscillation? Okay, so the nice thing about this problem is that you don't have to figure out what T is. It's given to you, which is really nice. And so in this particular case, we know from the Barkhausen theorem or condition, we know what is required for oscillation. The magnitude of T has to be 1, and the angle has to be 0. Or 360. Okay? So, um, so basically, we have to find out what RF needs to be in order for for oscillation, and also find out what the frequency is. The frequency is in here. Okay, so so if we want to look at magnitude, is that the magnitude equal to 1? So let's see this for a second. Okay, so just to look at the J's, the J omegas, we're going to have this. If I factor that in, okay, this right here, this is going to be real. That's going to be imaginary. So oh, okay. So if we were looking at if we were looking at angle 0, the imaginary goes on top, so we need that to be 0. So this part right here should be 0. So that means this piece right here would need to be 0. So in order for that to be 0, then that means that R over RF is 1/2, and so RF is going to be equal to 2R. So that's constraint in RF. Okay. And if that's 0, we can get rid of that right here, right? And if we set this magnitude equal to 1, then that means that even though this is going to be squared, it's going to be okay, wait a minute. So we're going to have omega c r going to be equal to 1. Well, we can get the squared off because it doesn't matter anymore, right? That's 1 over there. So omega is going to be equal to 1 over CR. Here's the other one. So this is the frequency that's going to oscillate at, and that's what RF needs to be for oscillation.
So doesn't that J squared mean that you're at a phase of 180 degrees?
This right here?
Yeah, wouldn't that be equivalent to a phase of 180 degrees instead of 0?
Okay, well, so if we look at the angle here, this is going to be tangent inverse of the imaginary over the real. So in order to get 0, we would need the imaginary part to be 0, right?
But your real is negative.
Huh?
But your real is negative.
But even if it's negative, it'll still be 0, right?
Wouldn't the negative be equivalent to being 180 degrees out of phase, though?
Okay, well, let's take a look at this. Okay, so oh, wait a minute. No, actually, yeah, not actually in this case right here. So okay, yeah. So the absolute value right here, or the magnitude, that corresponds to being 1. But this right here, it's not like you're taking the magnitude of that, but you are looking at like the real part and the imaginary part. And so here's the thing. If we have this right here, right? That's basically what this is. And you're trying to find out what is the angle of this, right? So what you're looking at is you're looking at this. And the A part is negative, but you have no imaginary part. And so for the angle, that angle needs to be B over A, because this is the imaginary part. And even though A is negative, the imaginary part is 0. Yeah, so we're okay. All right, so okay, so on this one, this is also dealing with T. Okay, so a Wien-Bridge feedback network is shown along with this loop gain, which is proportional to gain G. In order to achieve oscillation, what must G be? So in this case right here. So learning from our last T, which is kind of similar to this one, we know this right here needs to be set to 0. That's going to determine what the frequency is, but it's not asking for the frequency of oscillation. This right here, that must be set to 1. In order for that to be set to 1, the J omegas are going to cancel, the R and C's are going to cancel, so we just have G over 3. So G is going to be 3 in that case. I'm sorry, what? Oh, yeah, yeah. So if you want to find out the frequency, this part right here, you're going to set that to 0, and that will, I'm sorry, this whole thing right here needs to be set to 0. That's going to allow you to find out what omega is, but we're not trying to find the frequency. But if that's 0, if this whole thing is 0 right here, then you just have this numerator over that denominator. And then for the Barkhausen criterion, you need the magnitude of this to be 1 or the angle to be 0. Now, the nice thing about it is that these terms right here, the J, omega, R, and C, you have omega, J, R, and C up here. So those cancel out. All you have left is your G over 3. and the magnitude of that has to be equal to 1. Yeah. So so for this right here, a submit trigger is shown. So what is RF when this V0 is equal to VCC? So you know this comparator is going to either saturate high or saturate low, so that V0 is going to saturate to VCC or VEE, negative VE, one of those. So the question is what is Vref in both of those cases? So Vref, we could do voltage division, right? So that's going to be equal to, that's ground right here. Oops, that's ground. So it's going to be this divided by, both of those add together, multiplied by wherever that is. So it's going to be R1 divided by R1 plus R2 multiplied by V0. But this V0, it could either be VCC or negative VEE for either one of those. Okay. And so the other question is explain how a submit trigger avoids from being triggered by noise. So, well, first of all, can this be triggered by noise the way this is right now? Yeah, sure can. Like if there's a little bit of noise here, that's going to really change that reference. So what you have to do is sort of like shift it, right? By doing this. Put a capacitor here and a resistor. So this RC right here has a time constant. So as this capacitor charges, it takes a little while to get to where it needs to get to before it starts to discharging. And what this allows you to do is find out whatever your period is. So that's what this does. Okay, and this is your comparator and your Vref right here. If you do that, then you can get rid of that problem where it switches just due to noise, because what happens is you have the situation where you're going over here before you switch, and then on the way back, you come way over here before you switch, right? Wait a minute. I'm sorry. This is supposed to go lower too. Yeah, like this. So this right here is VCC. This right here is negative VEE. And these values right here, this is that beta times your Vref, whatever that is. Well, in that case, okay. So since you have that wider margin right here, then you're not switching just due to noise. If you didn't have this wider margin, then what would happen, just a little bit of noise here can switch you back and forth from this VCC level down to the VEE level, right? Because you don't have that much margin to play with, well, none to play with. Here, if this value along your VF is going back and forth a little bit, is not enough to go over to here to like cause you to switch.
So when you want us like how do you want us like to write that out on the fan?
Well, what you can do is say, in order to avoid the problem with noise, you can replace this right here with this kind of situation where you have this feedback resistor and this capacitor, right? And then you can explain, like if you had, I don't know, drawn this picture and explain how that margin is, as long as it's wider than the largest value of noise, that'll be enough. If you want to otherwise talk about I mean, yeah, just explaining, you know, why this would be problematic the way it is, and what you would do to change that in order to account for it falsely triggering or some unwanted triggering due to noise, by replacing that with a just drawing in the resistor feedback and a capacitor. Like, for example, you wouldn't have to draw this picture if you didn't really want to, but just, you know, explaining that would be enough, just up to that point. Okay. So write the nodal analysis equation for nodes 1, 2, and 3. Okay, so in this one right here, we have 3 voltages. So remember, for this we have, you know, your sources. That's the one that doesn't work very well. So you have your current sources, you have your conductivity matrix, and then you have your voltages. So these are vectors, and that's the matrix. Okay, so in our case, we'd have V1, V2, V3 for our voltage matrix. And for this right here, so let's do the first node. So first do your conductances. So we have an R2 going to a voltage source. You have an R2, an R4, and this capacitor right there. So you do your conductances. So it's your capacitor and your R, for your R, is it 2? Yeah, 2 and 4. So that goes for this first part, for 1. Now, here's the cross term. So for between 1 and 2, you have your R4. So that means for 2 and this right here, you have your R4, but you put in the minus there. Okay. And you also have some currents. So your currents go on your sources side. So you have this I2, right? Now the question is that a plus or a minus? If this was on this side, right, then clearly it would be a plus. But since we put it on this side, then it has to be a minus. And it would be plus because it's going out of the node. Like if your current's going out, if you just assign them all to be pluses, then you'll be okay with that. You also have this going in. That would be a minus if it's on the right-hand side of the equation. If it goes to the left-hand side of the equation, then that would be a plus. So that's the R1. I mean I1. Oops. And then for this right here, this current is, yeah, see this voltage source right here? It would be nice if it was on the one side going like this, but it looks like it's going this because it's going uphill this direction. So that means when it goes over here, it's going to be plus. And so that's going to be V0 and G2. Okay, so you have two sources right here. I mean, three sources. This is going to be a source going through your resistor. You have some current sources. Okay, but that's everything for node 1. For node 2, you have this, so R4, R7, and this in combination right here. So for R2, you have R4, R7, and those other two in combination, so it's R5 and R6. And they're in series. Okay, and for cross terms, so between 2 and 3, you have the R7. So 2 and 3, so that corresponds to this right here, and also this right here. So the cross terms of 2 and 3. Okay, what about sources? So for sources, we have this one going in. That'll be a negative on one side. When it goes to the other side, it'll be a positive. So I2 for positive. I don't see any other sources. So for R3, node 3, the last one, you have a R7. So what about this resistor right here? Does that really matter? Why? Yeah. This current is just plowing through whatever that is. Doesn't matter. So you guys see that. So this resistor, regardless of what it is not going to affect the amount of current passing through it. The amount of current will change the voltage drop across there, but it's not going to change the value of that current, is what I'm trying to say. So you have R7 and this capacitor right there, and that's it. So here you have your G7, and you have your capacitor, okay? And this one, you're sharing it with 2 right here that, oh, you already have it here, so it's fine. Yeah, so your source right here, that's going this direction, which is positive on this side, but we're going to put it on this side so it becomes negative. Then you just fill in the zeros. That's it. Okay. Yes?
So all these G's are just going over the resistance.
Exactly.
And would you care if we express it in terms of resistances?
Yeah, if you want to put it in terms of like 1 over R, that's fine.
Okay.
Yeah.
I've been like some voltage is equal to I1 times R plus some other current times R. We feel to express in that form. So B is equal to the I matrix, not the resistance matrix.
Wait, I'm sorry, I'm not getting you. So you're saying express it in a way that's not a matrix?
It could be expressed in matrix like B is equal to I times G inverse rather.
Oh, so you're saying like put this on this side?
Yeah.
Okay, so okay, so if you take this and put it on this side where it becomes the inverse, that would be okay. The only thing is that, of course, you don't want to do the calculation for the inverse, right? You just put the inverse -1 here when you put it on that side. Yeah, because, yeah, so this is what I think you're talking about, where this is the conductivity matrix, and it's that, and then here's your current sources, and here's your voltages. Is that what you mean? Okay, yeah. Yeah, but, yeah, so, yeah, you would put your G's here, put that -1 there. Otherwise, if it's a 2x2, it'll be easy to do the inverse. If it's 3x3, that's a little, it's doable, but it'll be time consuming. Yeah. Okay, so bipolar junction transistor shown. Draw its AC equivalent circuit. So for AC, what gets modified here, these become AC current blockers. So they block the AC current, so they become just short circuits at that point right here. And this right here becomes an AC bypass, where this becomes an AC ground. So it totally bypasses this resistor right here. So this just becomes short circuit right there. So well, you guys can see what happens here. These, so C1 and C2, they both become short circuits. And this whole combination right here gets replaced with just a short circuit. And what happens to this right here? Ground. This becomes a ground. Okay? So you just put like a ground there. That's all you need to do. If you want to change it around to say, well, if that's ground, then, and this is also ground down here, and you're starting at the same point voltage, then that R2 is going to be in parallel with that R1. If you want to change the circuit around to be like that, that's fine. If you're rushing and you just want to stick a ground symbol there, that'd be perfectly fine. Okay. Yeah, so in fact, if you wanted to, instead of like redrawing the entire circuit, you could just like stick a ground there, cross it out, put like a short circuit there, some kind of way, and make a short circuit right there. That'll be fine. Okay, so for the last one, design a sinusoidal function generator using op amps, resistors, and capacitors. So for this right here, of course, you know, we're going to use the oscillator that we've seen. So so we saw that in another problem, right? So here's the first stage. This gives us our rectangle wave. Okay? Well, the period is defined by RC, tau. Okay? So it takes time to rise up to your Vref, then it switches, then it takes time to go down to the next one before it switches. So it just keeps on doing that. So this is like your oscillator, but oscillates in a rectangular wave. Okay? After that, it goes into a what? A what? Well, yeah, the integrator. Yeah, exactly. Because the integrator will take it to a triangle, right? Because if this is just a square wave, And you're going to integrate this. So as you're going through time, you're going to integrate these little rectangles. And that's just going to build up linearly like a triangle. And then you subtract the rectangles, right? So that decreases it, but it's linear. Okay, so this next step just gives you this triangle wave type of thing. But you need an integrator for that. So for an integrator, okay, so let me ask you this. One second. Okay, so it's going to have a resistor and a capacitor. So do I put the resistor here, a capacitor here, or do I put the resistor here, a capacitor there? Resistor and feedback? Are you sure? For integrator? I believe it's capacitor. I believe if you put a capacitor here and a resistor there, then it's a differentiator, but that way it's a integrator. Oh, if I did do a differentiator, what happens in terms of noise? Like, why would noise be bad for a differentiator? Huge, yeah. Like, just think about this. You have this noisy signal, and you're going to differentiate that. So you got a slope here. Right here, you have a slope like that. So we're talking, this thing is going to, like, really, jump around. It's going to, yeah, it's going to be bad. Integrators smooth things out. Yeah. So so that's the triangle. So to curve out these sharp corners to more of like a sine wave, what comes next? Yeah, low pass filter. And low pass, because sharp changes are like high frequency types of changes. So what you want to do is have like a low pass filter. And it's sort of like an integrator, right? But it's like a leaky integrator. So here's your output right here. So that third output is this. This output right here is that triangle wave. This output right here is the square wave, or rectangle wave. Yes?
Why couldn't you look at a square wave to get sine?
Oh, you mean like go from this directly over to there?
Well, I guess I'm saying, why couldn't you just run a square wave through a low pass to cut off the edges, or to smooth out the edges?
I think, okay, if you did that, wow, that's interesting. So this probably could happen like this, because remember, this really depends on your period, right? So you might be able to end up something like this. So it wouldn't be too far off. And I'm guessing if you adjust your period just right, you can get it more to look like this a little more. But this is like even much closer to that. So it's like regardless of the period here, if you convert it to a triangle first, then you can get like that. So this is like really, if you're doing it this way, I think it's going to be period dependent of how close it's going to be like a sine wave.
The only frame of reference I have is the sharpness of the edges.
Yeah.
And they both seem to have really sharp. I guess like the sharp seems kind of arbitrary, but like it just.
Yeah, you're talking about like these.
Yeah.
Yeah.
What? I guess how much? I guess using that logic, would you not also end up with something that's closer to just a smoother saw wave? I mean, triangle wave than. Like, I guess if you're talking about getting that absolutely perfect sine wave, wouldn't you get errors with both? Like,
Oh yeah, you're probably not going to get a really perfect sine wave,
you just get
because
like a smooth triangle wave.
that would be my guess.
So is one of them better or worse?
Well, if you're trying to get something that looks more closely like a sine wave, then and do it inexpensively, then this is a good way of doing it.
Okay.
Only because this would be I think period dependent. And so if you reduce the period, then you can get these more to come together. So it's more of that cusp shape you're looking for.
Okay, so
Right.
you're saying like at a lower frequency square wave, you get worse results?
Well, yeah, you would have this sort of flattening that happens.
Yeah, I see what you're saying.
Yeah, because so the high frequencies of the corners would be rounded out, but but the straightaways, these parts, you couldn't avoid those. Yeah. Yes, you had a question, Alex.
Instead of an active low pass filter, if we use a passive low pass filter, would that be acceptable for the final stage?
Yeah, I don't think you need an active for that final stage. Yeah, that'll be okay. I don't see anything wrong with that. I saw another hand. Thought I did. No. Okay, so any other questions about any other question? Got the nodal, that. Oh, the first one? I'm sorry. So what's your question about the first one? Oh, so the input resistance, the output resistance, those are actually the same. This is going to be your input resistance. And a way to think about it is like if you're looking at it this direction, you're going to see this right here, that first resistor. And then same thing back here, all you're going to see is that output resistor. You're not going to see these other resistors in terms of input and output. For the gain, you have to work backwards. Now, this part right here, it says assume that the ROs are not negligible. That's where we had the resistor combinations. If they were negligible, all you have to do is say, oh, my gain would be A1 times A2 times A3, and that's it. You see what I mean? Yeah. And let me just show you why that's the case. So, for example, this first one right here, with that one right there, we had the Ri2 over Ri2 plus Ro1, and we did our voltage division with that. So you're starting at A1 VI1. I'm looking at it right here. You're starting right there. Okay, that's the voltage. That's output. The input is this right here. So V out over V in equals that. These two would cancel out, right? Now, if RO1 was negligible, you could say, well, it doesn't matter. Then that means that this over that just becomes 1. And so that's why if the ROs were negligible, you would just call it A1. Okay? Anything else? Okay, great. Okay, so that's it for today. Thanks for coming.